Okay, thank you everybody. First I have to thank Sebastian and Luis, like it was a very great presentation and I'm happy to see JStreamer doing Rust. We're all united in the media playing pain, so. Yeah, and they use num. Num is great. So, I'm here to talk about Sōzu. It's Sōzu, long O. It's a reverse HTTP proxy we built at Clever Cloud. Also rapidly, if I have something that works, yep, nope, let me just check, okay, it should be all right. So Clever Cloud, we do application hosting, like you do git push and everything will work and we do monitoring, upgrades, whatever. And I handle security and Rust mostly there. I've been doing big evangelizing there. And you can actually have Rust in production, like Iron or Hyper or whatever, on the server with our platform, so it's cool. So, shit doesn't work. I'm here to talk about Sōzu. So, it's a reverse proxy. So this is the thing that stands between the internet and your application. Like you could have like 10 virtual machines for your application, and you set up your domain to point to one of a few servers we have, and those will just dispatch the request to the backend machines. And so we built one, and what I said when I presented that thing was just, it should never ever stop. Because we have one problem we use HA proxy, which is a really, really great reverse proxy, but whenever we have to change the configuration, we have to restart that thing. And this is bad because we lose connection and we lose stability. So we started to do a proxy from scratch, and we started writing that in Rust because, hey, we're striking again. So very quickly, it's good when you have like a lot of application on the backend and there's virtual machine coming up and down and up and down, and here's a new application, a new front, and here's a new certificate, and it should handle all that very quickly at runtime. And it's quite great as well as a front-end server for microservices. And so, why is changing configuration at runtime hard? Imagine you have HA proxy, so this venerable, fast, very stable reverse proxy, and okay, you change the configuration and you add new backend servers, like you replace a virtual machine by a new one on different IP. So you will write a new configuration file, and you will tell to HA proxy, okay, so now this is the new configuration, like reload it. So it's quite smart, so it tries to not lose that many connections when it's reloading. But the thing is, it loses a lot of information. Like, when can I actually remove a backend server? Because I have removed that from the configuration, but actually there might be connection still going on. And I lose that kind of information. So we wanted to have something that's quite dynamic and that can handle that kind of case that's very, very specific. There's also another issue that we have is that we have to upgrade code at some point. And this is actually quite hard to do without losing any connection. And there's a last thing where Rust was a very, very good contender, is that we want to be able to predict memory usage. And as we know, garbage collection can make production a bit hard. And one of the ideas we wanted is to make it very easy to extend. And so we came up with this concept of Sōzu. This is this kind of Japanese fontaine, which is Japanese garden should be very, very quiet. And there's only the sound of the bamboo on the rock disturbing sometime very regularly. It's peaceful. You put it in production, you don't think about it, it's already there, it's all right. So, how is it? It's actually a GitHub repository with 4 cargo workspace with 4 projects. So there's the Sōzu library, which is like how you make a proxy. It's on the event loop and everything. Above that, we build the Sōzu executable, which will handle getting configuration and getting the upgrades and that kind of thing. There's the command library to talk to the proxy and send configuration changes and everything. And there's like the command line application that we made as an example of what we can do when you want to talk to Sōzu. So it's made with NOM, of course. Like building a whole HTTP parser in NOM is an interesting exercise. It uses Mule, not Tokyo, and we have support for HTTP1 and TLS, but not HTTP2 yet. So very quickly, NOM. We talked about it a few times. So it's parser combinators, it's macros, lots of macros. So parser combinators is just a way to combine pieces of code, and like you have code that will look like a grammar, but it's just code. It's not something that will generate something else afterwards. And inside, NOM parsers are very, very small. It's like hard to read. You have any function is like there's an input type, an output type, and an error type. And what a parser will return is either a result value with the remaining part of the input, or an error with possibly a pointer to a part of the input, or I don't have enough data to decide, which is very important. So, as I said, macros, it's very small and easy. This one will try to apply terminated. So you apply the alpha parser and then the digit parser, and if both are successful, you return the result of alpha. And when it's expanded, it will look a bit like this. So it's just a list of match arms. Well, actually, it looks like this because reasons. And the whole function is like that. But you don't have to see that. It's just very straightforward code. It's just a lot of boilerplate. So, as I said, we have the incomplete stuff. It's useful for streaming because you want to parse things and you don't know if you will get the whole data. Like, I will parse HTTP, but when I read from the socket, I will just, what I read may be stopping just inside the header. And so I have to make sure that it's not counted as an error, because I know that more data can be coming. So I have ways to split the parser and say, OK, so this part is not an error. I'm still waiting for more data. And the way it happens in NOM is I made this buffer abstraction, which basically I don't want to take the request or the response and build this whole object in memory that I will just write back to the network. I just want to look at the data coming and say, OK, so from here to there, I will give back to the backend, here to there and delete, and then I insert a buffer and whatever. So I have a behavior that just is based on that streaming buffer. So whenever I have a parser doing something, it will say, OK, there's a move, and it's like advance from these many bytes. And it will say, consume in the buffer these many bytes. And it will advance in the state machine and recognize, OK, now we got a request line, now we got the host, now we got a content size and whatever. And having a very local parser, a parser that's completely split that way, allows us to do like very fast streaming parsing. So it should never, ever, ever stop. It's a big goal. We're not there yet, but we have ways. So, few questions. Can we recover from failure? Like, failure will happen. How can we avoid losing connections? Because we will lose connections from different reasons. Like, if the process crashes, we lose all of the state. And how can we avoid restarting the process? Because it's one of the reasons we can lose connections. So that's when I choose to have a multiprocess architecture in Rust, in a proxy. First, I know that things will panic or crash, or like right now I have OpenSSL inside that thing, so I know there's still a big chunk of C. A lot can happen in there. So I was thinking, okay, can I just have a lot of threads inside one ROS process? And I said, no, different processes that I isolate directly. I wanted to have the zero downtime upgrades, and for this, I needed a multiprocess architecture. We'll see why. I want to be able to sandbox the processes, like you know that the proxy, most of the time, it will not need access to the file system. Like, it's just a pipe from the network from here to there and there to here. It does not need to see the whole system. And for a part of optimization, it's a good way to have a multiprocess architecture. So you would ask, like, why would I try to isolate stuff and sandbox and make multiple process to recover from crashes? And like, maybe I don't trust Rust enough. I trust Rust a lot there because I'm already putting this outside, but it's good to rely on different parts, and like the Unix philosophy on processes and file system and stuff really helps us at this point. So how can we avoid losing connection when we upgrade? Like, you have the code that's running, and you want to replace the processes and make sure that you won't lose what's currently running. So you just spawn new workers, and then tell the old ones, okay, no, stop accepting new connections. You will just terminate, we'll wait for the actual connections to terminate, and then you will close. And the master process will fork itself and keep the control over the workers, and then it should be all right. Well, in fact, it doesn't, because a listening socket has its own queue of coming connections, and if you say to a worker, stop accepting new connection, there might be still some in the queue, so you actually need to move the listening socket from one worker to the next. But with this architecture, we can have something that we just upgrade. Like, maybe you've seen like this nice GIF of people that are changing the tires on a car that's just moving sideways. Like, that's what we're doing with that. And it's quite cool. So we have a list of workers. Basically, we're just cloning everything. So it's the basic fork exec. We have, what's this? There's a small bar, wait, whatever. So we use using the fork infrastructure, also in the Nix crate, which is quite good. And the thing is, we want to have the different worker, master, and everything talking to each other, but we want to have a typed interface, because there we have the Unix stream interface, which is just a Unix socket, so it's just bytes. I send bytes, I receive bytes. It's not typed. So I built a channel abstraction of that, which basically there's a language that's JSON messages separated by null characters. I wanted to do a nice binary format, but the colleagues said, no, people will not build anything with that if you push binary formats again, so stop with that, use JSON. I know I'll be right in the end. And so that's something that's quite interesting is when I start a worker, I will send the configuration as a message, but then I will switch to another protocol. And I don't need to make something very complicated like with that. I just put, so that's where I should have used other colors, but I put the channel in blocking mode. I write the message. Then I put in non-blocking mode, and then I do into, and I just change the type of the message I can send and receive. So I'm using the same channel, the same buffers under the hood, but I'm just saying, okay, now this, after I've written the configuration, this channel will just handle other types of message. And on the worker side, I have the same thing. When I fork and I'm on the worker side, I will just exec a new process. I will tell to the new process, okay, here's the file descriptor for the channel. So it will start and know where it must talk. So when you fork a process, all the file descriptors will be shared. So if you have a Unix socket, you take both parts. So we have the server part, and the client part, and the parent will keep the server one, and the child will keep the client one, and you just have to know at which number it is. And once it's starting, it gets its file descriptor, makes a Unix stream from this, and receives the configuration in blocking mode, because we don't want to just receive a small part. We want to know, to get the whole configuration, and then it starts having a complete channel to talk with the master process. So now, can we change continuation without restart? There's another system for the master process. He exposes a Unix socket too. And like, you want to talk to the proxy, it's not listening to localhost, because anybody could be talking on localhost. It's a file somewhere on the file system, and there are rights to write or read from that thing. And this is where you will just talk to the proxy and say, OK, add a new front-end server, add a new virtual machine, remove this certificate, because we can change the TLS configuration on the fly. And like, here's a small example when we want to add a new front-end. Like, for this application, we want to redirect any connection to this hostname and this prefix in the URL that we call the pass begin. And so, OK, add the HTTP front. And then we send this message to the proxy. When we send the message to the proxy, at some point it will answer a message with the same ID. And there are 3 states for the message. You can have an error. You can have, OK, it's done. And you can have processing. Why do we have processing? Like, it's a configuration change. It should happen like right now. But let's say we're removing a backend server. OK, remove the backend server. And then the proxy will send, nope, I'm processing. I still have this many requests lingering. And I will send the OK when it's done, when all the connections ended. So this is really quite interesting, because we have the architecture based on the old Unixy process stuff. Now, how does it work under the hood? So we use an event loop. And I said we use Mule and not Tokyo. So why? Because I started this project a year and a half ago, and Tokyo did not exist. That's basically why. And there are, in the end, things that I couldn't do with Tokyo that I will do in Mule, but I talked about that afterwards. So Mule is, in the end, very, very, very simple. It's just you give a socket, and you say, I want to know when I can read or write from this socket. That's it. And so you have this poll object, and you register your socket to this poll object, and you call the poll method, and you will say, OK, I have this new event, like this socket is readable, and this one is writable, and this one is closed, and you handle the events. Like, the hard part is that, OK, you have to have your state machine that's meant to absorb, OK, know that this thing is readable, what do I do? Know that this thing is writable, what do I do? And there's the hard part of knowing how the events are sent. Like, maybe you've seen these terms, the edge-triggered events, the level-triggered events, one shot. Edge-triggered and level-triggered is something that's very, that comes from signal processing. But basically the way it works in ePOL is when it's level-triggered, like the socket is readable. And you will get the readable event over and over and over and over until you've read all of the data from the socket and there's nothing. And like the way it's done with asynchronous I/O is you read, and then you get an error that say, hey, if you try to read again, I would block. And that's how it's done. Edge triggered is, OK, this socket is readable. And you won't get the event again. And if you don't register that this socket was readable and you do nothing, I will not tell you again that it's readable. It's your job. And so there's a, I won't say easy, but there's a good way to handle that kind of thing. With two structures, like basically readiness and interest. and you store for socket the interest. Like, I want to be able to read from the socket. I want to be able to know if I get the hop, like it's closed, or I want to know if there's an error. And so when you get the event, like the readiness, like if I have a web server, my listening socket, well, the socket just opened, I want to know, I want to read data, so I have the interest RHE, so read, hop, and error. And when data comes in, I will most probably have the readable and writable events. And so I read, I handle my request, and now I say, okay, my new interest is write, hop, error. And then you might see that the readiness was already right, because like most of the time the socket will be writable. And so you write the data until you get the woodblock events, and rinse and repeat. So this is like the hard part to get, how to handle that. And in a proxy, it gets a bit more complicated because I have a front and a back socket. And so I want to read from the front socket, and once I read from the front socket, I want to write to the back socket. And once the whole request is done, it's the reverse. I want to read from the back socket and then write to the front socket. And so this is where there's most part of the complexity. And this is the idea of using Mule. Mule is very simple, but you have to handle the complexity. Tokyo hides and handles the complexity for you until there's a leaky abstraction somewhere and you have to do things yourself. But Tokyo is quite good. I have a lot of fun with that. So let me just check. I have quite some time yet. It's good because I have a lot of slides after the end of my talk, so I will just get into tools. But first, it's a young project, just starting like publicly talking about that, but it can be already quite stable. As you see with Mule, with the socket, with all the things I do, it's a good way to get into interesting networking code. And we made it so that it should be easy to build tools around. Like there's this Unix socket exposing the configuration language. You can make anything you want with that. Like you could make a small dashboard, a website to control the proxy. There's something I was explaining, like you can build Let's Encrypt around the proxy with that. The way you would do it is just, you tell the proxy, okay, I have this web server, so for this domain and this path prefix that Let's Encrypt will talk to, you send it to me. You tell Let's Encrypt to do the request. The request is done, you download the certificate, you send the certificate to the proxy. And you can build a lot of tools like that to automate completely the infrastructure. In the way it works at Clever Cloud, we have a RabbitMQ, a queue that gives the events for the configuration changes. And we have a small tool that's beside the proxy and gets the changes and sends them to the proxy. There are lots of easy issues, so if you want to contribute, and there are lots of things to do. Something I want to do like very soon is terminating the TLS at the backend server. Right now, all the TLS is done on the server and it's done with OpenSSL, and I don't want to use OpenSSL, but I don't have the time to switch to Rust TLS. Please help me. But we could actually terminate the TLS connection to the backend server. So the idea is that the proxy would just look at the first packets and see, oh, the SNI header is saying, I want to have this application. And so it would just switch based on that. But for this, I would need to parse the TLS messages, and no TLS implementation can do that, but there's a very nice French guy who did a whole TLS parser in GNOME, and I did not have to do it, and I will use its code, and it's great. Other things, like we want to add support for all of the configuration tools, like Kubernetes and etcd and whatever. Splicing is a quite interesting feature. Basically, when I've read the headers from HTTP and then there's a body, I don't need to read the body. I just want to say, okay, so this much data should go from this socket to this socket. Why do I have to read that to a buffer in my proxy and then write that to a kernel buffer. And so there's a splice syscall that say, okay, so you read to this kernel buffer and then you write to this kernel buffer, and this does not go through the user space. And you can get quite fast with this. And also there's HTTP2 support. So we need your help for that. It's called Sōzu. It's quite good. It's there on GitHub. And that's it. But since I have 10 minutes, I can either go to all the slides I had left because I thought it would be too long, or I can just answer questions. What do you think? Questions or slides?
I think a problem with questions is we don't have a microphone necessarily for people, so I would lean towards more slides personally, but...
Yep.
Yeah.
Okay. So then slides. So splicing. So that was the idea, like whenever you read from the socket, it gets to a kernel buffer first, like from the network card to buffer, and then you read to the user space, and then you write something else. And the idea is that you just do poof, poof, from one to the next, and it's done. About the memory usage, that's something I did not mention, but I had quite some fun with that. As I said, garbage collection can be an issue with that kind of project. So I want to have predictable memory usage. And at first, I saw like if I tried to allocate the buffers anytime a request was coming, it was quite slow and quite unpredictable on the response time. So I just started to pre-allocate. Like I come onto the machine and say, okay, so I take all the RAM. It's mine. Well, whatever. Most of the time, your proxy will be alone on its machine. So I take all the RAM, and then I will put bounds on the number of connections depending on the size of buffer I give. So I have 8 gigs. I have this size of buffer, and so I do a division, and it says, okay, this many concurrent requests. Why do I do that? Because when I don't have any more resources to give for new connections or new requests, I should just reject them. Because if I try to handle more that I can have on the system resources, I will just start to be slow, and I will slow every other request in concurrency. So I will just start dropping stuff instead of getting slow. Right? And there are a lot of optimization to do. Like at first, I did a very naive solution where there was a buffer for communication from front to back, and there was one for communication back to front. At some point, I was, maybe I can use the same buffer for front to back and back to front. They may not be used at the same time. Let's try. Let's put a lot of asserts everywhere. It works. So, yeah. What else do I have? Every worker is single-threaded. Why? Because each have their own memory, and like they're not sharing anything with any other worker. When you send the configuration to the master process, it sends the configuration to all the workers. They do not share anything. There's no mutex for that kind of thing. And no mutex, happy thread. Since I have different workers, I can just put them each on their own core. And when I have each of them on their own core, I have great data locality. That means like, if I had a process that would just jump from one core to the next, all of the data would have to be removed from the cache and move from one place to the next. If they stay on the same core, all of the important data and code is always in the cache for the CPU, and so we can get a great performance benefit. And there's another thing that's interesting with that is there are some kinds of network card. They have packet queues for each core. So instead of having one specific part of the memory where all of the cores go and take the packets, each core has its own part of the memory to get the packets, so they don't have to share that part either. And again, a great performance gain, and that was one of the ideas I wanted in the proxy at first. So what's left? Well, then it's like 30 minutes about what's good with blocking I/O and EPOL and all the other solutions. So I just stopped talking about this, and we can just talk about the proxy afterwards. Thank you.